implemented on a computer, the mathematical formulations are expressed as numerical optimization methods. This chapter describes the basic numerical methods for training a machine learning model. Training a machine learning model often boils down to finding a good set of parameters. The notion of good is determined by the objective function or the probabilistic model, which we will see examples of in the second part of this course. Given an objective function, finding the best value is done using optimization algorithms. Since we consider data models in d-dimensional real space, the optimization problems we face are continuous optimization problems, as opposed to combinatorial optimization problems for discrete variables. This video covers two main branches of continuous optimization: unconstrained and constrained optimization. We assume in this video that our objective function is differentiable. Hence, we have access to a gradient at each location in the space to help us find the optimum value. By convention, most objective functions in machine learning are intended to be minimized. That is, the best value is the minimum value. Intuitively, finding the best value is like finding the values of the objective function, and the gradients point us uphill. The idea is to move downhill in the opposite direction of the gradient and hope to find the deepest point. Let's consider the figure on the screen. This function has a global minimum around x equals -4.5, which has the objective function value of approximately -47. Since this function is smooth, the gradients can be used to help us find the minimum by indicating whether we should take a step to the left or a step to the right. This assumes that we're in the correct bowl, since there's another minimum around x equals 0.7. Remember that we can solve for all local minimum of a function by calculating the derivatives and setting them equal to 0. For this function, we get a corresponding gradient or derivative of L prime of x equals 4x cubed plus 21x squared plus 10x minus 17. Since this is a cubic equation, it will in general have three solutions when you have it set equal to 0. In the example, we can see that two of those points are minimum values, and the other is a maximum. To check whether a stationary point is a minimum or a maximum, we need to take the derivative a second time and check whether the second derivative is positive or negative at those stationary points. In general, we shouldn't be able to find analytic solutions, or at least we shouldn't expect to find analytic solutions. And so we need to find numerical approximations to those solutions. So we begin by taking an initial guess. Say, for example, x0 equals -10, and then we follow the gradient. The gradient indicates that we should go to the right. But how far do we go to the right? This problem is known as the step size. Complicating matters a little bit more is if we start on the right side of the deepest point, say, for example, x0 equals 0, following the gradient leads us to the wrong minimum. And we can see that by the arrows in the diagram. For x greater than -1, the gradient points toward the minimum on the right of the figure, which has a larger objective value. And while this example is a simplification in one variable, what we want to do is we want to work toward higher dimensional examples straight away. Gradient descent is a first-order optimization algorithm. To find the local minimum of a function using gradient descent, one takes steps proportional to the negative of the gradient of the function at the current point. Remember that the gradient points in the direction of steepest descent. Also remember the set of lines where the function has a certain value, for example, f of x equals c, are what we call contour lines. The gradient points in a direction that's perpendicular or orthogonal to the contour lines of the function we wish to optimize. So if we consider multivariate functions and we imagine a surface and a ball starting at a particular location x0, when the ball is released, it'll move downhill in the direction of the steepest descent. Gradient descent exploits the fact that f of x0 decreases fastest if it moves from x0 in a direction of the negative gradient. So if we let the ball roll down a small distance gamma, our new position x1 is going to be x1 equals x0 minus gamma times the gradient of f at x0 transpose. And if we do this, f of x1 is going to be less than or equal to f of x0. So in order to find a local minimum, f of x star, we first begin by selecting an initial guess x0. For a suitable step size gamma sub I, we iterate through x sub I plus 1 equals x sub I minus gamma sub I times the gradient of f at xi transpose. Doing this results in a decrease in sequence. F of x0 is greater or equal to f of x1, which is greater or equal to f of x2, and so on. And eventually this converges to a local minimum. As an example, we consider this visual of a quadratic function in 2 dimensions. Starting at an initial location x0, which is -3, -1, we iteratively apply the gradient descent algorithm to obtain a sequence of estimates that converge to the minimum value in the purple area of the diagram. So we start at -3, 1. We plug that number and the gradient into our gradient descent equation, and we come up with our second approximation, x1 equals -1.98 and 1.21. We then plug that point into our algorithm, and that gives us an x2 equal to -1.32 and -0.42, and so on. Notice that at the beginning of the algorithm, our steps are relatively large, and we gain a lot of ground quite quickly. Gradient descent, in general, tends to get relatively slow as we get closer and closer to the minimum. As we said earlier, choosing a good step size is important in gradient descent. If the step size is too small, gradient descent can be very slow. If the step size is chosen to be too large, gradient descent can overshoot, fail to converge, or even diverge. Thus, there's 2 simple rules that we have to think about. If the function value increases after a gradient step, the step was too large. Undo the step and decrease the step size. If the function value decreases, the step could have been larger. Try to increase the step size. Now, while you might say that undoing a step seems to be a waste of resources, using this heuristic actually guarantees monotonic convergence. Now, a technical theorem here says that if we assume that f from Rn to R is convex and differentiable, and that the norm of the gradient of f minus the gradient of y is less than or equal to some L times the norm of x minus y, that is, f is Lipschitz continuous with Lipschitz constant L greater than 0, then gradient descent with a fixed step size gamma less than 1 over L satisfies f of xn minus f of x star is less or equal to the norm of x0 minus x star squared over 2 gamma n. That is to say that gradient descent converges and that f of xk minus f of x star is less than epsilon with order 1 over epsilon iterations. In this example, we're going to apply gradient descent to the function f of x equals x squared cosine x minus x over 10. We'll start with an initial guess of x0 equals 6 and a step size of 0.2. We've graphed the function on the right. Our first dot, x0, is at x equals 6, and we'll follow its path down the gradient. We begin by finding the derivative. F prime, in this case, is equal to 2x cosine x minus x squared sine x minus 1 for 10. And so, our xi plus 1 is equal to xi minus gamma f prime of xi, which is equal to xi minus 0.2, our step size, times our derivative, 2xi cosine xi minus xi squared sine xi minus 1 over 10. The iterations x values are 6. We plug 6 in for xi, we get 5.588. If we plug that in for x, we get 5.037. And you can follow this along down the pink line on the gradient. 4.512, 4.169, 3.978, and so on. After about 10 or 11 iterations, we get a lot of good similarity between our numbers, indicating that we're starting to converge. And so we end the algorithm when the difference between successive approximations, in this case, 3.718 and 3.712, is quite small. So in this case, less than 0.006. In our next video, we're going to talk about a different optimization algorithm.